quenching and compaction, but related to environment more. So first speaker is Simona Mei, and who will talk about what happens to quenching in dense environments.
Hi, thank you to the organizers to give me the opportunity to give this talk, which is based on 3 papers, one with the Candles collaboration and 2 with the Carla collaboration and my student Gael Monroe. So, first of all, why we are interested in quenching in clusters and protocluster at z equal to 3 is because at this time, this is the evolution of the main progenitors of clusters today. For a comma, Virgo, and Fornas cluster, you see that 2 and 3, at this time, we have the first progenitors can be called clusters, so 10 to the 14 solar masses, while all the other progenitors in the hierarchical model are more objects at 10 to the 13th, so group of clusters that will eventually collapse to form the cluster that we observe today. Also, their distribution is very different. So this is the virial radius, the red circle of a cluster at z equals 0 for a cluster of 10 to the 15 and 15.5 solar masses. As you see at z equal 2, you don't see the compact form that they have at z equals 0 at present, but they are more extended on a larger scale that is more of the order of 10th of megaparsecs, where you continue to see these small groups that eventually will collapse to form the structure that we see today. So 10th of megaparsecs is not the scale that we have on deep images, for example, with the HST, where we have more scales of a few megaparsecs, and we have tens of megaparsecs only on large scale surveys, for example, with Spitzer. So to see these objects, really what we are seeing is always small parts of them or the main progenitor that just stands up being the most massive. So keeping that in mind, you won't expect many of these objects given the rarity of these large surveys that find them, and also the variety of techniques. And here is how many we are. So here are the bunch of clusters, the many clusters up to z equal 1. You see as you go towards z to 3, the rarefied, this is the one cluster at z more or less 2.5, and then it continues to rarefy up to the highest detected z equal 8. And the techniques change a lot, so you detect clusters with X-ray and SZ up to z equal 1, and then here you have to rely on optical and far infrared and Lyman-Bragg galaxies on different techniques that don't select homogeneously as you are selecting at z less than 1, where you have X-ray or SZ that have a selection function but are selecting homogeneously up to that. So all these different techniques tell us different stories about quenching, because you can select on passive galaxy over density, on star-forming galaxy over densities, on star-forming and passive with Spitzer using the Popovich technique. So you're mixing up different kind of galaxies depending on the redshift where you are, and each selection tells you a different story. So you have a non-star formation cluster course with Spitzer techniques, high passive fraction in cluster course if you select on passive galaxy over densities. You have 50% passive fraction in cluster cores if you select on star-forming galaxies, or violent star-busting cores if you select with Herschel and where you observe dust, or a mixture of star-busted passive galaxies. So depending on the selection, we are still at the point in which we know different stories, and I want to tell you 2 of these stories using one object in the Candle field that is the deepest field that we have. So the deepest observed, the protocluster that we observe today, and another story using the sample from the Carla observations, that is a sample of 16 cluster and protocluster between 1.5 and 2 and 3, sorry. So the first story is about this object, who is a protocluster at 1.84. There are 2 structures, one a protocluster and a group at 1.9, that we observe in the ultra-deep field with the Candle collaborations. As you see, there is a peak, is a 20 sigma towards the background, with respect to the background, and an estimated mass of 2 plus or minus 1.8, 10 to the 14 solar mass. So why do I call it protocluster and not cluster? Because it's a 10 to the 14 solar masses. One reason is that it is a protocluster, so it is a structure that is very, is a peak of 20 sigma on the background, when I observe star-forming clusters with spectroscopy from candles at 3D HST, but is also part of a larger structure if we expect from the simulation, when at the same photometric ratio you have many of these groups. So they are just collapsing to form a cluster at present. And second reason is because of this galaxy population that is not yet formed. Is galaxies have only few have an ATG morphology. Most are very disturbed, star-forming galaxies. Only half of them are compact and have an ATG morphology. Most have companions, tidal tails, and irregular morphologies. And the ATG fraction, 50%, and 80% is star-forming. So they're not the passive ATGs that we usually find in cluster. So not only the structure is assembling to form a cluster today, but also its galaxies are not yet the classical passive ATGs that we observe today. So 8 on 10 are star forming, they show 3 emission compared to the very few in cluster at Z less than 1.3. So they are compact, they are ATG, and they are star forming, so they are blue nuggets. So what we expect is exactly what we see. There is no red sequence, so this is their distribution in mass. You see that the masses are, only few are more than 10 to the 5 solar masses. We are in the ultra deep field, so we can reach masses of 10 to the 9 solar masses. And most of them are blue nuggets with masses between 9 and 10 to the 5 solar masses. This is the red sequence we would expect from passive evolution from Z equal 1. Only 2 galaxies have a 4,000 Breck. All the other ones don't show anything else than the emission line. So the 2 structures have not yet formed a red sequence. And this is the first time that we observe these blue nuggets that you expect from the hierarchical model, since you know that the ATG is formed from very less massive compact galaxies that will merge to form the ATGs that we form today. So the progenitors of today ATGs in clusters. So this is a very interesting object. There is no evidence for the AGN from Chandra observation, so there is no AGN to stop the star formation, or what we can observe. And the star formation rates from the O3 emission, so here we have assumed the O3 H alpha emission, the Connecticut law, equal 1, and the Connecticut law, are on average of 10 solar masses per year, so there is no either a starburst, nothing. They're just there, they just star form at the normal rate in the optical rest frame, and they just normal, compact blue nuggets with a star formation of few of solar masses per year. Their sizes, so this is the mass-size relation for star forming and passive galaxy at present, in the present universe on SDSS from Bernardi et al. Our sample are the triangles and the circles. The triangles are the star forming, the red circles are the passive galaxies. And here are the relations from candles from a sample at the Z equal 1 from the Lei et al. 2014. And you see that also their masses and sizes are very much consistent with the relation we observe at Z equal 1, and they just lie on the same mass size relation. So they have the same sizes of the same mass as the passive ATGs at Z equal 1 that are on this continuous red line. These other diamonds and squares are other 2 clusters at Z equal 2, the Newman et al. 2014, the Strazzullo et al. 2013, the go-back cluster. And as you see, we are on the low mass size in the mass size relation, while there are more massive galaxies in the Newman et al., we are in the same low mass size at the go-back cluster. There's also 20 sigma over densities with respect to the field. When we plot all these, we see that the size of the blue nuggets are consistent with the size of massive passive galaxies from the Delay et al. Sample that are clusters between 0.8 and 1.6, that are the 3 stars. This is gamma, is the normalized radius at the mass of 10 to the 11 solar masses. You see that it's almost constant. The blue nuggets we have seen, they are more or less here, and the relation of this sample, that is the yellow point, is enlarged by the presence of the two 4,000 Bragg galaxies, who are a bit larger sizes. There are these two that are already on the high end of the distribution. And these two are the other two clusters in Newman et al. And the Goba. And you see that all clusters show passive ATGs, and in this case, blue nuggets and two only large galaxies that are larger than the field. This is from Newman et al. 2011 for massive ATGs, passive massive ATGs. So larger sizes, evolution is flatter in the I universe, that might indicate a faster evolution of these galaxies in the clusters. So to confirm these observations, now we need a larger sample, because here you have only one object observed very, very deeply in the Hubble deep field, but is only one object, actually just a piece of an object that is collapsing. So we're going to larger samples. The most deep observed sample with the HST is the Carla. So Carla was a sample of clusters selected around radio loud AGN. As you know, radio loud AGN hosts in preference high over densities, and they were selected by Spitzer colors, so using the Popovich 2008 technique, that is IRAC 1 minus IRAC 2 larger than minus 0.1. All the sources selected with this method will have a redshift larger than 1.3, and if you observe an overdensity around the radio loud AGN, which you already know the redshift, you can then follow it up and see how many are the same redshift of the AGN. So the program was a snapshot of 420 radio loud AGN between 1.3 and 3.2 in redshift, and 200 more or less were observed. This is their distribution in pink. This is the distribution of the field. You see how their distribution goes towards higher density than what is expected from the field. And the objects that really interest us are the ones that are 2, 3.5, 5 sigma from the field. So the sample is divided is selected with different overdensities, and the very peak of the overdensity, that are all the objects, 20 objects, a sigma larger than 5, were followed up with HST. So looking for overdensity of galaxies at the same redshift of the AGN, that since it's already known, was easy to plan, so that there was a UC-HiPACC imaging and spectroscopy to orbits with two different orientations to have green spectra, and 16 of the 20 that have at least 5 galaxies in the UC-HiPACC field of view at the same redshift at the radio loud AGN, with an average of 10 galaxies each, and some classes have more. So we have two confirmed cluster protocluster at z equal 2, and the highest confirmed overdensity at 2.8. We're still analyzing the samples in terms of morphology, but we already have results on the star formation that I will show today. This is an example of a spectra. So you see, usually there are green spectra, so they are no high resolution, and they show clearly emission lines. So knowing already the redshift of the GN, in this case Z 1.676, is easier to identify the emission line you're looking for, and depending on the redshift, you will change emission line to H alpha, O3, and O2, depending on which redshift you are observing. These are the star formation rate derived from H alpha, O3, and O2 for the entire sample. We had around 500 spectra, which only 67 are cluster members of quality A, that means have at least 2 emission lines. 18 of quality B plus means they have emission lines and Spitzer colors that are right of being at that redshift, and around 60 that have only 1 emission line and they are not detected with Spitzer. So we cannot really tell if they have the right Spitzer colors. These limits are the limits of the 3D HST. So you see that is at the same depth as we expect, because they're more or less the same observation times as the 3D HST survey. And in this diagram, they just fill up this region and just double the sample of cluster and protocluster between 2 and 3. So this is very important sample with HST and Spitzer, and in part multi-wavelength data. So I will present the results on the two confirmed clusters at z=2 that were the first who were published in the Noiro et al. 2016. This is how they look like, very sparse. And the confirmed members are the green circle, and the red star is the AGN. So you see there is no high concentration as you see in local clusters. They are sparse around, but you can tell that with around 10 members each, these are overdensities are significant. There is the AGN, very large Spitzer overdensities, and 10 confirmed galaxies in a space of an order of 1 megaparsecs square. So what about their population and quenching? Actually, what we find is that these objects, even if they are both very high Spitzer overdensity, even they have the same number of confirmed members, etc., they have very different stellar population. And we select passive galaxy on the UVJ rest frame diagram that are these square red objects. The AGN is the diamond. All the diamonds, sorry, the AGN, no, the AGN is not here. The diamonds are the confirmed members in both cases, and the red points are the Spitzer selected object with color larger than -0.1. You see where the passive rest sequence should be from a Bruce Wallace-Charlotte 2003 from the gray lines, and this is a 3 sigma range, and the blue-red sequence, always a 3 sigma, is from Mei et al. 2009, that is just passive evolved from z=1 to z=2. Here is an SPP model, so that you just have a burst of star formation and passively evolved to this redshift, and the yellow line, these are tau models that you see, they span a range of star formation just exactly where the blue galaxies are. So they are the star forming galaxies with that formed with different tau models. So you see that we forget about all the other symbols, just concentrate on the passive galaxies. You see that there is a population of passive galaxies in one object, there is not this population in the other object, and is exactly where you would expect a passively evolved red sequence from z=1 to z=2. So this is already a cluster with an evolved red sequence, just where we would expect it, while the other one does not have any red sequence objects. Only two that are classified as passive in the UVJ diagram, but just at the limit of what we would expect as passively evolved red sequence. So very different population in two objects with the same overdensity. And we're now analyzing the other 14 to see which one is the percentage of which kind of object in this very high Spitzer overdensity. What is the star formation rate in the 16 confirmed protoclusters? So from the emission line, using a Kennicutt law, we obtain star formation rate. This is the star formation rate normalized to the area as function of the distance from the AGN. You see that in the center, at all redshift, there is an enhancement of the star formation, as Brondue et al. 2013 found. So even if there is an AGN in the center, in the core of the cluster and protocluster, you find an enhancement of star formation, and actually the number of star formation confirmed members grows as you get closer to the AGN. So you have more star forming galaxies close to the AGN. What is interesting though, and this is probably because there is an AGN, or perhaps because there is a lot of dust, you see that if we look at the star formation mass diagram, and compare it with the field from Dadie Whittaker et al. This is a Whittaker et al. 14. I think that Gael made a mistake in the picture. So you see that when comparing galaxies at the same redshift, here you have the sample at 1.5, 2, and 2.5. You see that our galaxy are always lower with respect to the main sequence at the high masses, plus than 5, 10 to the 10 solar masses, so that they look already more quenched So you have to compare the red points with this line, these light points with this line, and these red points with the less yellow line. So you see they are always on the high end. You always observe quenched galaxies with respect to the main sequence in the field. So they already start, the star-forming galaxy already start to be quenched. We are now following these clusters with the ALMA and NOEMA. We have 2 programs with already data on 2 clusters, a 1.4 and 1.6, and we are waiting for the phase 2 on the NOEMA data to have the other cluster. So how to go ahead with this kind of studies? Euclid will give us 10,000 square degree on the sky with thousands of clusters and protoclusters observed in this field. This is what we will expect for an object of more than 10 to the 14 solar masses and 5 10 to the 14 solar masses per square degree. On 10,000 square degrees, you have thousands of these objects. And this is what will be the Euclid mass limit with respect to other sources. You see, in a case of Euclid optimistic, that is Euclid plus LSST, we will go down at redshift equal 2 to masses of the order 2 10 to the 14 solar masses. So we will observe these protoclusters up to z equal 2. And even in the case of pessimistic, with DES being the optical counterpart for photometric redshift, you see nothing changes much, because what counts is the depth of Euclid in the infrared. And you see that at this redshift we will reach as much as deep as SPT pole, but much deeper than other surveys that will be available on the next decade. So the conclusion, we find compact star-forming blue emission line progenitor local mass ATGs in a protocluster at Z1.8 in the Hubble ultra deep field. So they became compact before becoming red, so their blue compact will become red. And in the Carla clusters, we find the variety of stellar population, but we find the optical emission line SFR lower than in the field for the most massive galaxy, so that they are star-forming galaxies, but they are already starting to quench with respect to the main sequence. And remember, there is an AGN, a very powerful AGN at the center of these objects. And we will know more when we will complete the whole sample analysis that is in progress right now. So, thank you.
As this graph shows, redshifts around 2, a third of the red sequence galaxies are actually dipped. You've been focusing on very compact values, but you have information on morphology, and you have some bits in these protocols.
For those, so you mean for the Carla sample? Yeah, we are starting the morphology analysis right now. Yeah, so we already started. Yeah, Gael just graduated, so he left the work not completed. Somebody else just took it, is Stefania Modeo from our group, and I have to verify results before I can tell you which kind of galaxies they are. But we are doing this, and we are both doing it automatically and visually to be sure to have the right analysis. Yeah. Sorry. Yeah. This is why I said because it might be. So what Gael tried to do is to assume an attenuation that is the double of the attenuation that is always used by 3D HST, and even putting a double of the attenuation, we are always lower than the rest sequence. Because these are massive galaxies, so I expect to have more dust and to have more attenuation and high redshift. So we asked him to just double the attenuation, and he always finds star formation rates that are lower than the rest sequence. So we were also worrying about that because of the results from Raphael and the fact that you find this large dust content and star bias. So we see perhaps we don't see it in the optical and we want to check it. So we just continue to add that artificial attenuation to check that.